Statistics Unit 6, Lesson 1, How Many Children Are in Your Family? Today we're going to be discussing discrete and continuous random variables. Okay, so what we did in class is that I asked everybody how many total children are in your family, and then we counted that up. This is one particular example. For instance, we had 30 people in this particular class, and I had 3 that had 1 child, 7 that had 2 children, 9 that had 3, and so forth and so on. As you can see that my random variable is here that I'm describing as my x, and x is equal to the number of children. And this whole chart is my probability distribution. The probability of each occurring is 3 out of 30, 7 out of 30, 9 out of 30, and so on. And the distribution just means how it is separated, how many each one has. All right, so is it a valid probability model? In order for it to be a valid probability model, the 2 things you have to remember, and on the test, this is number 1, you have to remember that each probability has to be between 0 and 1, because 0 is 0% and 1 is 100%. So each one of these has to be between 0% and 100%, and they all are. So that's the first thing. And the second thing is that these all have to add up to 1, which you can see in this work that I showed, 1, because 1 basically is the same as 100%, so 100% of the time. So because it adds up to 100% of the time, or 1, yes, those 2 things are met. The reason 5.7167 is not a possible value is because x is what we call a discrete random variable. A discrete random variable is when you cannot have part of the value for the x value, for the x that you're talking about. Since x is the number of children, I can't have part of a child, so I can't have 5.7167 in one of my actual values here. Now, if I ask you how many average children I have, then I am allowed to describe it with a decimal. But if I'm asking if x could equal something with a decimal, no, because that's an actual category. Px greater than or equal to 3 just means the probability of having 3 or more children versus the number 6, which is p greater than, which just means more than. And of course, to find it, you just add up the probabilities just like this. Okay, let's look at y equals the time it takes for randomly selected family to get ready for school. Is 15.71767 possible? And yes, because I can have 15.7167 minutes. I can have a part of a minute and any parts of a minute. If you're 5 feet tall and then you have a growth spurt and now you're 6 feet tall, you hit every single value in between 5 feet and 6 feet. You didn't just wake up one day and you were 5'4" and then 5'8" and then 6 feet. You just you woke up during the day, yes, but you grew during the night or something. You have to you hit every single value. All right, so this wants you to do it with a normal distribution, and this is showing you how to do it with a table. I'm going to remind you how to do it with the calculator as well. So this is asking you to do this with a mean of 35 minutes. And a standard deviation of 12. So you can see my model is 35 is the mean and standard deviation is 12. We could continue to draw the model out here, which would be 35 plus 12 is 47, 59, 71. And then, of course, going further down, 35 minus 12, again, is going to be 21. So I got to get it a little further. There we go. 21, and then here, and then 9, and then this is actually going to be negative 3. So again, it's okay that it's negative. It's just a model, and a model isn't necessarily perfect in showing what we have a reality. It just kind of gives us a good trend of the data that we're doing. Okay, so that's what we have, and then the reason this is shaded here is because I asked what's the probability it gets ready in 20 minutes or less, and so that's where my shading is. And to find my z-score, I have my observed value of 20 minus my mean of 35 divided by my standard deviation of 12, and I get negative 1.25. And if you remember, when I look in my z-score table, I look up for negative 1.2 and then 0.05, and when you find that value on the z-score chart, that's when you get the 0.0156. The other way, of course, you could have done it is normal CDF. A normal CDF, you can remember, get with menu, statistics, distributions, and then normal CDF. Where your lower bound is your most left shaded area, and so it's off the chart, so it's negative infinity. But the inspires don't like negative infinity unless it's a cast, so we put negative 9999, or doesn't recognize, I guess. And then upper bound is just the highest it's shaded, which is my 20. And then the mean and standard deviation, of course, that's my mean, is 35, and the standard deviation is 12. If you put those values in, you will get something really similar to 10.56%. Okay, so the main things that I wanted to make sure that you got for today is you see that this is the probability distribution, where the top row is my x, my random variable, and ours particular was how many children are in the family, and the p of x is the probability that each of those occurs. Remember the difference between discrete random variable and continuous random variable. As a discrete random variable is a fixed set of values with gaps. So I have 1 child, 2 children, 3 children, and there's gaps in between those numbers. Continuous, it's like the minutes, the time. There's no gaps. It takes on every single value. These here are probability distribution functions. This one here, this first one, is a uniform function where it's always the same. And this one, of course, is a normal model. And the probability is just the area under the density curve. So what I'm looking for when I'm asking what's the probability, I'm just looking that if I threw a dart at this, what's the probability I'm going to hit this red shaded area if I was for sure going to hit the graph itself. And that's just the probability. It's just seeing the area that's shaded under the curve. Okay, let's look. Do you want to build a snowman? First of all, it's asking are these discrete or continuous, and you can see the reason that these are discrete is because number of snow days, I can't have a 0.75 snow day in the school. It's either I'm off, the way it's describing it, I'm either off school or I go to school. So this is going to be discrete. The next one asks if it's what probability of x equals 0 is going to be. If you notice, it's empty, but we know if it's a valid probability model that all of these here, the sum is going to equal 1. So you can see in the work that I have here is that I add all of them up, and then I subtract it from 1, and that's where I get 0.33. If there are more than 6 snow days in a given year, that it's going to be extended. So what's the probability that happens? So more than 6 snow days are the 7, 8, 9, 10. So that's why you're going to see the probabilities of 4%, 2%, 1%, and 1% added up to get 8%. And then the next one says, write the event that the school ends before 11:15 a.m. Well, this here is telling you 11:15 a.m., 10 a.m. is when it's considered a late start. And so 11:15 a.m. is 75 minutes after 10 a.m. So we're going to say, okay, we're going to see what the probability is. And the way you're going to do that is like, okay, 75 minutes. I'm wondering how it's greater than 75 because it says, what's the event that it ends at 11:15 or before 11:15? So I want to know less than 11:15. So I'm saying 75 minutes times 1 out of 180, that one particular day. Why 1 out of 180 is because I have 100. It told me I have 180 days of school. And so each day I have a 1 out of 180 chance in order for it to end early. Because it's the same probability for each day if you read it up and see what it says. Okay, I hope that helps, and I'll see you at next lesson.